So when I think about this mountaintop that we're trying to reach in the field of solid state physics, which is analogous to material science, we get to that mountaintop when we can build materials one atom at a time, and we start looking at each other and thinking, okay, what's next, right? We've achieved literally anything that we can do because now we can position individual atoms to make the material work exactly how we want it to work. So there's a strategy that I would use. I use these charged projectiles that I can accelerate at some target at about 80% the speed of light. Or I can go a lot slower and I can make it have a small enough projected range such that it sits at an individual atom site that I want inside of a material. And so I use that. It's a form of research called radiation solid interactions, where I can use energetic particles of radiation to actually control the positions of atoms in my material. It's not just seeing individual atoms and moving them around, but it's also calculating the vibrations of atoms at the atomic scale so I can get information on thermal properties. It's also looking at the optical spectrum so that I can see how good, if I position this atom, it is for modern day electronics. The first fusion reactor is trying to be scaled and built by Commonwealth Fusion Systems. If you were to build this fusion reactor, how much do materials age and how do their properties degrade over time? The worst thing about a nuclear reactor is having the components fail and then you get some catastrophic event that happens. There's a reason that we spend so much money and do this investment to use this microscope because it answers these fundamental problems so that we don't get these catastrophic events.